Let's dive deeper into the monitoring and controlling of EHVDC, extra high voltage direct current transmission lines, covering the technical details and the engineering principles behind their operation. 1. Monitoring EHVDC transmission lines. Real-time data acquisition. Efficient monitoring requires precise and timely data from the transmission line and its associated equipment. 1. Voltage and current sensors. Measure DC voltage and current levels across the system. These sensors are typically installed at converter stations and critical points along the transmission line, and provide data for calculating power flow, ensuring it stays within design limits. 2. Temperature sensors. Conductor temperatures are monitored to avoid overheating, which could reduce the line's lifespan or cause outages. And modern systems use fiber optic temperature sensors for higher accuracy and real-time reporting. 3. Insulation monitoring. Partial discharge detectors analyze insulation health. High partial discharge levels indicate potential dielectric breakdown risks. And continuous monitoring identifies developing faults before they become critical. Digital monitoring systems. 1. SCADA. Systems act as the backbone for monitoring, enabling remote access to field data. These systems can visualize trends, issue alarms, and interface with control systems. 2. PMUs. Though traditionally used in AC systems, PMUs in EHVDC systems are integrated with AC systems to measure phasors and ensure dynamic grid stability. 3. Line current differential monitoring. Evaluates the current at both ends of the line to detect anomalies, ensuring minimal delays in fault detection. Health and fault monitoring. 1. Line fault detection. Detects ground faults, line-to-line faults, and open circuits using protective relay algorithms. Traveling wave and impedance-based methods are commonly employed for fast and precise fault location. 2. Arc detection. Optical sensors coupled with high-speed electronics can detect arcs caused by physical damage or insulation failure. Early detection prevents catastrophic damage. Environmental monitoring. 1. Transmission lines traverse diverse terrains, making environmental monitoring critical. Weather stations collect data on wind speed, ambient temperature, and humidity. And lightning detectors identify potential strike zones and send preemptive alerts to mitigate damage. 2. Controlling EHVDC transmission lines. Control systems ensure the safe and efficient operation of EHVDC lines under various conditions. Power flow control. 1. Converter stations. HVDC systems use power electronic converters at either end of the line. Rectifier stations convert AC to DC at the sending end. Inverter stations convert DC back to AC at the receiving end. Controls at both ends maintain DC voltage stability and power flow as per load demand. 2. Current control. Control systems regulate DC current to avoid thermal overload and line sagging. 3. Dynamic voltage regulation. Voltage source converters, VSCs, allow dynamic adjustments to voltage, especially beneficial in weak grids or during transient disturbances. Stability and oscillation control. 1. Automatic generation control, AGC. Balances generation with load demand, maintaining frequency stability in interconnected AC grids. 2. Supplementary control. EHVDC systems often include damping controllers to suppress low-frequency oscillations that arise from grid dynamics. 3. Fault recovery. Adaptive algorithms quickly restore power flow after disturbances, reducing downtime. Fault management. 1. Protective relays. High-speed relays ensure fault detection and isolation within milliseconds. Advanced schemes, such as line differential protection, use high-frequency communication for precise and coordinated fault management. 2. DC circuit breakers. Traditional AC breakers are unsuitable for DC systems due to the absence of zero crossing. Modern DC breakers use energy absorption methods, e.g. varistors or superconductor-based mechanisms, to interrupt current. 3. Power reversal. Unique to HVDC systems, the ability to reverse power flow, change direction, is achieved within minutes, offering flexibility during grid emergencies. 3. Advanced technologies in EHVDC AI and machine learning. 1. AI models analyze historical and real-time data to predict potential issues, such as equipment failure or insulation degradation. 2. ML algorithms optimize power flow, especially for systems integrating renewables. Wide Area Monitoring Systems, WAMS. 1. WAMS integrates data from multiple PMUs, providing a unified view of grid dynamics. 1. This helps in optimizing HVDC power transfer based on AC grid stability conditions. Energy Storage Systems. 1. Battery Energy Storage Systems, BS, integrated with HVDC systems provide fast response power during high demand or contingencies. Condition-based maintenance, CBM. 1. Instead of scheduled maintenance, CBM uses real-time data to perform maintenance only when needed, reducing costs and downtime. 4. Challenges in EHVDC systems, insulation, and dielectric stress. 1. EHVDC lines operate under steady-state voltage stress, which accelerates insulation aging. 2. Solid-state and gas-insulated systems require enhanced materials and real-time monitoring. Converter station complexity. 1. Multi-terminal HVDC systems are becoming more common but introduce challenges in power flow management and fault isolation. 2. Coordinating multiple stations requires sophisticated control algorithms. Cybersecurity risks. 1. The integration of digital control systems increases the vulnerability to cyber attacks. 1. Implementing robust encryption, intrusion detection, and firewalls is crucial. Key benefits of advanced monitoring and control. 1. Increased reliability. Proactive fault detection minimizes downtime. 2. Improved efficiency. Real-time adjustments optimize power flow. 3. Flexibility. Dynamic controls support renewable energy integration and address variable demand. 4. Cost reduction. Predictive maintenance and better fault management reduce operational costs. EHVDC systems are evolving rapidly with technology, becoming an essential component of modern power grids. Let me know if you'd like further details or a deep dive into specific components like VSCs, converter topologies, or real-world examples.